Welcome to the next lecture on data formats. Today we are going to talk about another hierarchical data format, and that is JSON. In the last lecture we talked about XML, which was also an hierarchical data format, but today we'll talk about JSON. JSON was designed as a lightweight, language-independent, easy to read and write by humans, and easy to parse and generate by machines data format. It's hierarchical in nature, so in this it is similar to XML, but it is less wordy and it is used in different contexts than XML. It has, of course, a standardized media type and a file extension. And you'll find more than 100 formats used on the web which use JSON as a serialization. When I talked about XML, I talked about the fact that XML is often enough referred to as a meta format or a host format, which means that it by itself defines the proper syntax and the constructs you can use. But typically, within JSON, you define your own data format by specifying the names of values and types of values that will be found in documents used for specific reasons. For instance, GeoJSON for geodata uses JSON as a host format or a meta format and specifies how geodata is to be used or written in JSON. And let's go a bit deeper with JSON. We'll explain what JSON standardizes or what it looks like and what it is made of. And we'll start with a JSON string. So a JSON string is always Unicode when transferred over the network. And there are special characters which are escaped using backslash. I will accompany those explanations of individual JSON parts with so-called railroad diagrams, which help us visualize a grammar. So in this case, when we read the railroad diagram, a string starts with a double quote, and if we go straight, we end again with a double quote, and that's it. So that's an empty string. However, we may go down from the opening double quote, and then we either have a regular character or a backslash, and then we see a list of characters that need to be escaped by a backslash. So that's again a quotation mark or a double quote, then backslash and slash, and then backspace, form feed, line feed, carriage return. So those are new line characters, and then also horizontal tab. And in JSON, we can also escape any character using 4 hexadecimal digits. So that's what you can see in the last correct example on the left, which actually says JSON string, but it is escaped using Unicode escapes. Besides the escapes, we can see the escaped quotation mark in the example and then a regular string in the correct examples. And in the incorrect examples, we can see a string containing a new line which is not escaped. This is invalid in JSON. And we see a string with a quotation mark or a double quote, which again is not escaped. So this is an invalid string in JSON. Now, JSON documents contain not only strings, but also numbers. And there is also a railroad diagram for how a proper number looks like in JSON. And again, we'll see that 0 is a valid number, and that may be it according to the diagram. We also may have -0, which is valid JSON number, but it still means a 0. And then we have integers, we have floating point or decimal numbers, and then we have floating point numbers denoted by an exponent, present in the number, and the exponent can be lowercase or uppercase. There are some incorrect examples of numbers. For instance, number a decimal number which instead of the decimal point has a comma, that's incorrect, or a fraction, also incorrect, or a number that is written as a string is a string and not a number. Besides strings and numbers, JSON also contains typically quite a lot of white space. White space is used in JSON for indentation, and it doesn't mean anything, it is just there. And white space consists of space, line feed carriage return, which are new line characters, and horizontal tabulators. Though all those are used for indentation, it is not recommended to mix different types of indentation in one document, such as what can be seen in the screenshot in the slide. So this is not recommended. However, I show it to you here to see what can be a white space in JSON. Then a JSON value actually consists of white space before and after the actual value, and then the value can be a string, a number, then we'll skip object and array for now. Then it can be a true or false value, which are Boolean values, or it can be an explicit null value. So those are simple values, and when we want to use more complex structures in JSON, we may use an array, which is just a list of values. Start with a bracket, end with a bracket, and inside we have values which contain white space, and the values are delimited or separated by a comma. There is no restriction on the data types of the individual values of an array. So those arrays you can see in the slide are both valid arrays. The first one has numbers, strings, and a null value in it. The second one has only numbers, but both are valid. One notable thing is that a JSON array can be a root of a JSON file, which we'll see later. But a JSON file can have a JSON array or a JSON object as a root. Which brings us to a JSON object, which is the most complex structure we have in JSON. It starts and ends with curly braces, and it may be empty, which is the first line of the railroad diagram, or it may contain a list of key value pairs or name value pairs in JSON terminology. The separator of the name and the corresponding value is a colon. The name value pairs are separated by a comma. And after the last name value pair, there is no comma. So these are the rules of JSON. We can see examples of JSON objects in the slide, and because a JSON object is one of the types of a JSON value, we have nesting, so a value of the name value pair can be another JSON object. And this is how a complete JSON looks like. As I mentioned, we have two JSON files or JSON documents here. One has a JSON object as a root, and one has a JSON array as a root, and both are valid. And this is it. JSON is quite a simple serialization format. Nevertheless, it is specified by a series of specifications by different standardization entities. So the first mention of JSON is in the 1999 specification of ECMAScript, which later became JavaScript. Then it was separated from the JavaScript language and became a language independent format. And from 2001, it is being developed at json.org. And as the time goes, the JSON format became standardized by IETF as an RFC, and also by ECMA, which is the European-based standardization agency. And the goal here is for both of the standards to actually standardize the same language, but I recommend taking a look at both of those documents and see how they look like and how they differ. There is one fun fact regarding the 2014 RFCs. As you can see, there are two, and as you can see from the number, they are quite close together, right? Because the first RFC is 7158 and the other RFC is 7159. And also when you read through the standards, especially through the later ones, you'll see that those two are used interchangeably or together. And IETF supplies a tool for comparing two RFCs. And if you take a look at the tool, and there is a link in the speaker notes, you'll see that there is just one slight difference between the two RFCs. The first one was mistakenly annotated by the published date or published year 2013. And the second one was correctly annotated 2014. But since the first one with the wrong year was already published and RFCs are published and never taken away, they had to correct the mistake by publishing another RFC. So those two RFCs, if you take a look, are exactly the same. And the only difference is the year they were published. And in fact, they were both published in 2014. However, the first one incorrectly states 2013. So this is quite an extreme case of standardization, where once a standard is published, it is never taken down, even if the error in it is as small as a wrong published year. In 2017, the main change in the ECMA standard is that UTF-8 encoding must be used in JSON when JSON is transmitted over network, which in our case is always, because we publish JSON data typically to transmit the data over network. So this means, in fact, that UTF-8 encoding is mandatory for JSON. Again, there was an RFC in 2017, and both the ECMA standard and the latest RFC do specify the same language. Now, once we have JSON explained and specified, what we can do with JSON, well, we can of course make sure that our JSON is valid. There are online tools for that. So it is quite easy to validate your JSON, and also to, as you can see, for instance, in the right example, to process JSON or view it in a way where you can collapse objects and so on. So you can browse the JSON file quite comfortably. Now, where JSON is actually used are typically web APIs. So for instance, here we see an API of GitHub, which is the repository of open source software. And it has an API which you can use, for instance, to list the contents of a repository and list commits and so on. And it uses JSON as a data format. Another usage example of JSON are check standards for open data, where, for instance, for a touristic point of interest, there is a standard saying how those data should be represented. And again, it uses JSON as the format to do so. There is a quite simple command line query tool, JQ, which you can use to query and transform JSON files. So its usage is in the middle of the slide. It's quite simple. It uses a sequence of filters where data is passed from one filter to another using a pipe symbol. And in our example, we see that we have a JSON array document, and the first filter takes the first item of the array and passes it on. And the second filter actually creates a new JSON object with a message key and a commit message value. This is the query, which actually gets the commit message value from the input data, and a new JSON key name with the commit name value, which again is a query, and it takes this value from the input data. And the result is in the bottom of the slide. So here we see a simple JSON transformation. Another example of software where JSON is used is, for instance, document stores such as Apache CouchDB, which is a document database. You can store a large number of JSON documents in the database and then retrieve them. Or also JSON is often used for storing a search index. So for instance, Apache Solr, or maybe its alternative Elasticsearch, you may know, those use also JSON as a representation of the search index. There is one slight modification used quite often, and this is JSON lines. And this is used when you want to have one file containing multiple records that are supposed to be processed one by one, so in a streaming fashion. Then in regular JSON you would have to have one array full of items, or you would have to have an object with a list of key value pairs, but it would still be one object, one array. So typical libraries would work with this as with one object, and that might not be convenient. That's why there is this very simple specification, JSON lines, which works like you see on the slide. It is a text file which contains JSON objects and JSON arrays, one per each line, and those JSON objects or arrays in themselves or by themselves are valid JSON objects or arrays. So this is an alternative to basically having a folder full of JSON files. So you can have this in one file with the JSON-L extension, and you can process this line by line. This can be also used as an alternative to CSV files, which we will talk about in another lecture. So CSV files are files for representing tabular data or relational data, and they typically have rows and columns. But the problem with CSV files is that they do not support structured values very well, and JSON does. So for lists of records where some of the values are structured, it might be beneficial to actually use JSON lines instead of CSV, because you can take each line and run a JSON parser on each line, and you know that you can parse the JSON lines file like this without any problems. Also, JSON lines is a bit more typed than a CSV file, because in a CSV file, when you do not use any CSV schema, everything is a string. However, in JSON, we already know that we can have a typed number or Boolean value, or a string, or an array, or a structured value. So yeah, this is JSON lines. Might be beneficial for some use cases. For instance, in machine learning, where you have very large files with very many records, and the records are a little bit structured, then it might be beneficial to use JSON lines instead of a CSV file. And since we talked about XSLT in one of the previous lectures, there is support for JSON in XSLT 3.0. So XSLT is a transformation language for XML, which is another hierarchical data format. But since both XML and JSON are hierarchical data formats, they can be transformed from one to the other. And in XPath 3.1 actually, which is used in XSLT 3.0, there is the JSON to XML function, which takes a JSON string on the input and it transforms it into a corresponding XML representation, which then can be processed using typical XSLT. And the way it works is shown in the slide. So on the left, we have the input JSON text, and on the right, we have the resulting XML structure. So a JSON object represents or corresponds to an XML map element, and then each key value pair or name value pair gets represented as an XML element named by the JSON type, which is used in the value. The key attribute contains the name of the JSON value, and the contents of the element contains the value which was in the JSON. There is a special element for the null type, as you can see here. And when you have a JSON array, in that case, there is the array XML element with, again, the key specifying the name of the value containing the array. And the contents of the array is, again, a sequence of individual elements. This also works the other way around. So if using XSLT, you manage to create a representation like what you can see on the right, there is also the inverse function, XML to JSON, to which you can feed an XML representation of JSON like this, and it will actually produce the JSON string. So using these two functions, you are able to transform JSON also using XSLT, which is quite a strong language with lots of functionality. Another technique I want to mention when talking about JSON is JSON pointer, which is quite a simple technique, which allows us to point to a specific value in a JSON document using something which is quite similar to XPath, but much simpler because there is only one way to go through the JSON document, and that is from the root down. The JSON pointer can be represented as a JSON string, or it can be represented also as a URI fragment, which is useful when pointing to a certain value in a certain JSON file on the web. But before we get to that, let's take a look at some examples of JSON pointers. So on the right, we have our JSON document, and in the table on the left, we see three examples. The first one starts in the root and selects the value represented by the key value pair, in which the key is up to date. So the result of this JSON pointer is the true value. Then if we point to cities and go to London, then the result is the array of how far it is from London to other cities. When we have an array and we want to go inside using JSON pointer, we do that by array indices, which are 0 based. So cities, Brussels, 0, and 2 points to the text London. So this is JSON pointer as represented in a JSON string. Now, if we want to use it as a URI fragment, we need to know where our JSON file is located on the web. So what is the URI of the JSON file? So we can now see that on the top. And on the bottom, we can see how a JSON pointer, the last one we talked about, can be attached to a URI as a URI fragment. So in this case, we point using a single URI to a specific value in a specific JSON file. And there is one detail worth mentioning, and that is that if the JSON key was to contain a slash, which is a reserved character in JSON pointer, then this slash is to be escaped, and it is to be escaped using tilde and 1. And since tilde is used for escapes, it also needs to be escaped, so tilde is escaped as tilde 0. So these are the only two escapes in JSON pointer, and that's it. As with XML, there was the XML schema language for describing schemas of actual XML documents. With JSON, there is also a schema language, JSON schema. And the question may be, why do we need a schema for JSON? And the motivation is again the same as always when we talk about schema language for a certain data format. So for instance, here we have a JSON object and there are keys product ID, product name, price, and tags. We may think that we know what those keys actually represent, but all we have are those key IDs and nothing more. So that's a big assumption that we understand the data just based on the names of the short names of the keys. So the first natural task of a schema is to annotate the data, to explain what is actually in the data, what is used in what keys, and what the values mean. And when the data is explained using schema, so additional information is given, there is also a second motivation, and that is validation. So is the data valid against a certain schema? Is the JSON file that I received valid, or is the JSON file that I produce valid? So in this case, the annotation could serve the task of explaining what exactly is, for instance, a product ID. Does it correspond to something in real world, and so on? And the validation has the typical tasks like is a product name required? Do I need to fill it in? Can the price be also 0? So can the product be for free? The tags, are those all string values, or can I have a number as a tag, and so on? So these are all questions that are answered using a schema, and in case of JSON, the language for that is JSON schema. So it is a proposed IETF standard, and it is under development since 2009, and it is still not finished. There is a number of draft versions out there, and there is also a whole website that you might want to visit that also contains the book Understanding JSON Schema, based on which I'll give you now the tutorial to JSON Schema. Right, so on the right side, we have an example of how the JSON Schema looks like. As we can see, JSON Schema is a JSON document, and it contains the identification of the JSON Schema version used. Then it contains identification of the JSON Schema itself using an IRI, and then the rest of the schema follows. To get a better understanding of how JSON Schema works, let's take a look at our original example, which is now on the left side of the slide, and we'll try to annotate the data that we have. So we had a JSON object, and we assumed that it represents a product, and now the schema tells us that it in fact represents a product, and it is a product in a catalog. So the schema provides a title and a description for our JSON object. And in addition, it says that the type is indeed an object. So it, for instance, shouldn't be an array. So here, our sample JSON object validates against this particular JSON schema. Now, you might have noticed that some of the JSON keys in the schema start with a $sign, so those are schema keywords. Then there are schema annotations, typically a title and description, annotating the data, and then there are validation keywords. So the key value pair type object serves validation purposes. So using this, we can actually use the schema to validate the data instance, and here we just validate that the instance is a JSON object, and in this case it is valid. If we were to change the instance into a JSON array, then we would get an error because the schema says that the root is an object. Now let's take a look at what we have in the data. We have a product ID, a product name, a price, and tags, which are an array. We already know that the JSON object indeed should be an object, but let's talk a bit about what the object should contain. For this, we have the properties construct of the JSON schema. So here we have the schema from the last example, but we added the properties key value pair, and inside the properties object, there is product ID defined and it is annotated. It has a description and it says that the product ID is the unique identifier of a product, and there is a validation keyword, again type, and it says that the product ID is an integer. In addition, in the object definition, we say that product ID is required by using the name of the key value pair product ID in an array, which is the value of the required key in the schema. So here we can read the schema as there is an object, it has the product ID property, which is an integer, and it is required. So again, properties and required are new validation keywords. And let's continue. We'll talk about the product name key value pair. So we'll add product name to the properties in the JSON schema, and again we'll say this is the name of the product, and the name of the product is a string. And because in our representation we want both product ID and product name for each product, we add the product name key to the required array. And we continue on. We talk about the price, which is a number. In this case, we say that it is just a number, it is not an integer, which means it can be a decimal number, as in this case. And we say that it is the price of the product, and there are some additional constraints that can be used on numbers in JSON schema. We show the exclusive minimum, so the price needs to be positive. It cannot be a 0. So this is the answer to our original question, whether the price can be 0, and now we know that it cannot be 0. There are other constructs that can be used to constrain numerics, and those are maximum, minimum, and exclusive maximum. And there is multiple of constraint, which can constrain a number just to multiples of a certain number. So those were numbers. And let's move on to the tags part of our example. Here the validation gets a bit interesting because there are two modes in which JSON arrays can be validated. The first mode is called list validation, and basically it describes a schema for all or certain items of the list. So the array here is a list of items, and for all or some of the items, the schema specified must apply. So for instance here, for the tags array, we say that those are tags for the product. It is an array, that's fine, and it has items. And all the items are of a type string. In addition, we say that there is at least one item and that the items need to be unique. So it is not possible to have, for instance, the home tag twice in the array. When talking about list validation, we already used items and min items. We can also specify a maximum number of items, and we talked about unique items. In addition to this, we may say that this array contains some items which are valid against a certain schema, and again we might add constraints on how many of those items need to be there in the array. So if we used, instead of items, we used contains, then the schema would need to apply to at least some of the items of the array. So this is list validation. It doesn't matter, for instance, in which order those items are validated and so on. So we validate this as a list of items. On the other hand, we may view the JSON array as a tuple, which means that the positions are very relevant and meaningful, and we might want to use a different schema for item in different positions. So for instance, here we want the first item of the tuple to be a number. The second item we want to be a string. The third item, a string with an enumeration of values. So it needs to be a string, but it also needs to be one of the values enumerated in the schema. And the same goes for the fourth item. And like this, we proceed with the validation. So in the first case, we have a number, a string, then a string which corresponds to one of the enumeration possibilities, and then another string which again corresponds to some of the enumeration possibilities. So the first JSON array is valid. The second array has a number, then a string, but then it has a string containing the text drive, which is not listed in the enumeration. So this one is not valid. The next array has just one item, and the first item is not a number, so it is also invalid. Now we have an array with 3 items, and in our schema we have 4 items specified. This is okay. So the types correspond, and the fourth one is missing, but this is fine. And it is also fine to add another item to the end of the array, because there we do not say anything about the rest of the items. We only speak about the first, second, third, and the fourth item. We can know that the schema will use tuple validation because the value of the items key is an array. So in this case, it is in the tuple validation mode. However, if we do not want to allow to add additional items, we may specify that by saying additional items false in the schema. And in this case, the last JSON schema is now invalid because it has 5 items and we only want 4 items. We also might want to say that any additional item needs to be a string. So additional items actually can contain another schema, which is then used for validation of all additional items. In this case, all additional items need to be string, which is okay with the last example. If we changed these additional items to a type number, then the last example here would again become invalid because the last item is a string and not a number. So now we talked about numerics, we talked about properties of objects, and we talked about arrays. Let's talk about nested JSON objects because those are quite a key construct in JSON. So here we'll add another key value pair to our example, and this is dimensions. And dimensions will be a structured value, and it will be another nested JSON object. And we want to create a schema for it. So inside the properties key of the object definition, of the root object definition in the schema, we'll just add another key, dimensions, and we'll define it as of a type object. And therefore, we again specify its properties, which are length, width, and height. All of those are numbers, and all of those are required. So the example on the left here is valid against this extended schema. Now, what may happen is that some parts of the schema are to be reused in multiple other schemas. In that case, it might be beneficial to take this part of the schema and make it so-called external. So take a part of a schema describing, for instance, an object describing latitude and longitude, which means a coordinate, geocoordinates. And because we know we want to reuse this in multiple schemas, we will publish it as is on the web on the IRI described by the ID key here. Then in our other schemas, we may reference this external schema using the $ref key and the IRI of the schema as the value. When the JSON instance is validated and we come to the warehouse location key, then we know, or the validator knows, that it needs to go to another external schema, which looks like this, and the JSON instance is valid. Now, we omitted a little bit string values. So string values are the most common values in JSONs, I would say, and therefore it is necessary to focus on them a little bit more. So one of the constraints that we can use on strings are string length constraints. So for instance, here we have a string value which has 2 or 3 characters, and therefore when we use a string that has 1 or 4 characters or any other number of characters, it will be invalid. Also, another common type of validation of string values is using regular expressions. So in JSON schema, we are able to define a regular expression pattern and use it to validate, for instance, a telephone number here. It's an American telephone number, and the first 2 examples are valid and the second 2 examples are not valid. When talking about strings, we need to mention other formats like dates and date times and so on. In JSON, we know that there is only the string data type, and there are no data types for dates and times and the other formats that are mentioned in this slide. So all those are actually JSON strings when viewing them as data types from the JSON point of view. So if we want to specify how this particular string should look like, we need to specify its format. And the format has a separate JSON schema keyword, format, and this is the list of formats that can be used. So there is a string format for dates, times, date times, durations, emails, URIs, IRIs, host names, IP addresses, JSON pointers, regular expressions, and so on. So all those can be used in JSON schema to specify further the string data type. For instance, here we have a string data type which has the IRI format. It is in addition restricted using a regular expression pattern, and what you can see here is another annotation, which is examples. It contains an array with example values that can be used as values of this particular JSON key. So this is very beneficial for developers when they view the JSON schema and they also see some examples of valid values. Besides objects, there are Boolean values, so true and false, those are valid. True as a string or a number, 0 is invalid. And then there is the null value. So if we say that a specific key has the type null, it means that nothing else than a null value can appear in its place in the JSON instance. So this is a way of enforcing that some value is always null. So those were simple functionalities that can be used in JSON schema to validate JSON instances in a quite straightforward way. But there is also possibility to combine multiple schemas into one, which is then used to validate a certain value. So the individual schemas can be combined using the logical connectives any of, all of, one of, and not. When we use any of, it means that the value needs to validate against at least one of the schemas in the any of array. When we use all of, then all of the schemas need to validate the certain value. If we use one of, then at least one of the schemas in the array needs to validate the value. And if we say not, then the value must not be valid against any of the schemas in the array. So for instance, the first example is impossible because we say that a certain value needs to validate against all of the schemas in the array, where one of the schemas says that the value needs to be a string, and the other schema in the array says that the value needs to be a number, which is never true, so this schema is impossible. The second example says that the value needs to be either a string with length up to 5, or it needs to be a number 0 or larger. And the last example says that the value must not be a string. Right, so let's take a look at how schemas can be extended or built upon. So this is what we already had. we had the schema on the right validating the instance on the left, where we had a street address and a city and a state. And all of those, the street address, city, and state, are required by this particular schema. What if we want to extend this address by another key value pair, and we want to validate that key value pair? We want to add, or we can add another key value pair right away, but it wouldn't be validated because the schema doesn't know about the new key value pair. And if we add a new key value pair and we want it to be validated, we of course can do it by taking the schema, copying it, and adding the newly added value. But there is a way of actually reusing this schema that we already have and just adding our new value. And that is the all-of construction that we just talked about, because we can combine all-of and we can combine it with the reference to an external schema. And for instance, here, if we want to add the type key with business or residential possible values, we can do it by saying that the instance need to be valid against all of the following schemas. And the one is the original one referenced as an external schema, and the other one is the one validating just the added key value pair. So like this, we can extend schemas with our own additional properties, for instance, by using all of and saying that the value needs to be valid against the original schema and then against our new schema describing the newly added properties. Another thing we can say is in the JSON data is non-JSON data. Non-JSON data is typically described by a media type, which we already know. That's the list of types managed by IANA. And when it is, for instance, a binary data, it can be encoded again using base 64 encoding, which we have already seen when we talked about XML. So for instance, here we want to say that a certain value is a string and the content media type is text HTML. So we are saying in the schema that the value of this value, that this JSON value is actually an HTML document. And like this, we can, for instance, encode or include an PNG image in a JSON file by encoding it using the base 64 encoding. Now, if we have a schema and a JSON instance, we can use a JSON schema validator to actually validate the instance against that schema. There is one quite popular, for me at least, validator, a JSON schema validator.net, which works quite nicely even with external schemas. So I recommend you use this one when you are going to validate your JSON files against your JSON schemas. Now we are going to talk about JSON-LD. JSON-LD is actually a RDF, Resource Description Framework, serialization in JSON. And why do we need to talk about it? Well, we now know what JSON is, but we also know that it is quite insufficient for publishing data, for instance, on the web, where we lack the support for global identifiers of things, IRIs. It is impractical to link from one JSON file to another because there is no explicit support for that. So JSON has its use cases, for instance, for web APIs, but when it comes to describing data and linking data, it is insufficient. And therefore, we want to talk about how to make JSON data actual link data. And JSON-LD is the way to do this. And JSON-LD was created with the JSON-focused developers in mind. So the goal of JSON-LD is actually allowing viewing JSON data as RDF for those who are interested in it, while shielding regular JSON developers from all the complexities of the RDF data model. So now we are going to talk about how to add features to regular JSON so that it covers all of RDF, and it can be viewed as one of the RDF serializations, but maintaining the JSON features that regular JSON developers are used to, and hiding the complexity from them as much as possible. Right, so we'll start with a normal JSON that looks like this. We have 3 key value pairs. There is name, there is homepage, and there is an image. So we may assume that this is a description of some person. And we want to make this data RDF. So what we'll add is what we'll call a JSON-LD context. The JSON-LD context will contain all the information necessary to enhance the JSON data to make it RDF. So in this case, this context contains a definition that the name key corresponds to schema.org/name predicate. The image key corresponds to schema.org/image predicate, and the homepage key corresponds to schema.org/URL predicate. In addition, it says that the values of homepage and image are IRIs of resources and should be treated as such. But if we are a normal or regular JSON developer, we may ignore what is in the @context key, and we still see a regular JSON file. JSON-LD is a web standard W3C recommendation, currently in version 1.1. It is developed at the JSONLD.org website, and as you can see, the JSON-LD 1.1 specification is quite recent. Before that, there was JSON-LD 1.0. But the goals of JSON-LD have not changed, just the possibilities of how to map the JSON data into RDF have been extended. And so we'll start with something simple. We'll want to say that the person described in the JSON data is identified by an IRI, because that's what RDF is based on. And we can do this by introducing the @ID key, which value contains the IRI of the resource being described by a certain JSON object. Now you may have already noticed that the JSON-LD keywords all start with the @ symbol. So this is true. All JSON-LD keywords start with the @ symbol, and you may spot them by this. So like this, we already say that we have an object that has an ID. The name key corresponds to the schema.org/name predicate, and the value is a string, in this case containing the name of the person. Now, the next thing we want to say is that the JSON object actually represents something of a certain type. So we need to specify the class to which this object belongs to, or we may call it a type. So in these examples, we have restaurant. It's actually a brewery. So it's a restaurant and a brewery, and we say it by using the @type JSON-LD keyword here. So we know that our first example is a JSON object. It identifies an RDF resource, example.org/places #breweats, and it is of a type restaurant. The @type keyword generates the RDF type RDF triple. So now we know it is a resource of a type restaurant. In the second example, in the lower left side of the slide, we see that, there may be multiple types to an object, and we can use the JSON array for that. So in the second example, we know that this is a restaurant and a brewery. Now, I talked about hiding the complexity from regular JSON developers. The first step to this is aliasing. So we might hide the mapping of a word to an IRI in the context. And we'll do this a lot. We'll try to hide as much as possible in the context, which then can be ignored by the regular JSON developers. So here we say that whenever we use restaurant, it means schema.org/restaurant. And whenever we use brewery, it means schema.org/brewery. And we say this in the context. Therefore, in the JSON data, we might use the @type keyword, but the array now will not contain two IRIs, but two regular words, as if it was a regular JSON representation. But since or when we look at this data as RDF, so we take the context into context, we know what IRIs the classes have. So this actually generates two RDF statements or RDF triples of the RDF type. Now we might want to specify a base IRI and use just relative IRIs wherever IRIs are used. And we can do this again in the context by using the @base keyword. So for instance here, when then ID is an empty string, it is actually an empty string attached to the base. So we are talking about the document.json-LD file here. And we say it's just a simple document. Similar to base is the @vocab keyword, which specifies the default vocabulary. The default vocabulary construct can be used when we use just one vocabulary in the whole JSON-LD file. This is quite typical when we use JSON-LD for annotation of web pages, because there we typically use the schema.org vocabulary, and therefore we might say this in the context. We might say that all of the JSON-LD file uses the schema.org vocabulary, and therefore when we use the restaurant word in the type or the name as the key in the JSON data, we know that these two need to be attached to schema.org/. And like this, we again may generate RDF triples. Now, sometimes it might happen that we actually do not want some part of the JSON file to be present in the resulting RDF graph when the JSON-LD is loaded. And we might do that by specifying that certain key is null in the context. When we do this, then when data with this key appears in the JSON file, it is ignored when loaded as RDF. Now, another step towards getting rid of those long IRIs is compacting, which is similar to prefixing in other RDF serializations. So here we actually define, for instance, the fov prefix, and then we use it in places where IRIs are expected. So for instance, here in the context, we define the fov prefix, and in type, we use fov:person, and we know that it is the full URI of the fov:person class. And we use fov:name as a key, and we know that this is the fov::name URI. So like this, we generate actually a blank node, a resource with no IRI out of this JSON object, and the RDF type triple going to the fov::person IRI and fov::name predicate going to the string value. Now, another thing we might want to define is the data type of the JSON value. Now, when we talked about JSON, we talked about the JSON value types, which were string, number, boolean, null, array, or another JSON object. So later in JSON schema, we talked about specifying formats of the JSON strings, and from RDF we know that we want to use the XML schema data types for specifying the data types of string values. And this can be done again in the context by specifying for certain key in modified, in this case, both the ID, which specifies the URI of the predicates to be used in RDF, and the type keyword, which specifies the IRI of the data type of the values connected using this predicate. Which means that in the regular JSON part of the data, we see modified and the standard XML schema datetime data type and nothing else. But the context tells us which predicate this is using and which data type this is using. And we know it's the XML schema datetime. Now, a typical feature of JSON files is embedding, which means that we have objects in other objects. So here we have a person, Manus Pony, who knows, and the value of knows is another JSON object of a type person and name Greg Kellogg. So here we have on the top level we have a blank node with both name and both knows, and the value of both knows is another blank node of a type person and name Greg Kellogg. So here the JSON nested objects work quite naturally as embedded RDF resources. Now, when we are talking about a nested JSON object, we may also utilize scoped context. So in a nested JSON object, we may redefine the JSON-LD context. In this case, we have, again, a person with a name. And on the top level, the name key is mapped to example.com/person#name. However, then when we go into details, we want the name key be mapped to something else. And the something else is example.com/organization#name. So we have the same JSON key, which is name, but we have two different meanings in RDF. One is a name of an organization and one is a name of a person. And we redefine to which predicate the name key is mapped to using a scoped context within a JSON object. So those were JSON objects, and we also talked about data types of values. We also need to talk about languages, because we know that in RDF, every text value which is in a natural language needs to have a language tag specified. So in our JSON data, we also want to be able to specify the languages of the values in the JSON file for which there is no support in JSON. Again, we'll utilize the context for this, and we might specify a language for all text values by the top level @language keyword in the context. So in our example, we are saying that all text values, unless specified otherwise, are in Japanese. Then we might use the @language keyword also in the definition of a key mapping. So name here is mapped to the X name predicate, and the values will not have language tags. The null says it will not have language tag, which means the value will be an XML schema string. Then for occupation, we map occupation to a predicate, but we do not specify any language, which means that it will be in Japanese, since that is the context-wide language. And then we have occupation_n. For that, we say that the value will be in English, and occupation_cs. And here we say that the language will be Czech. Later, in the regular JSON data part of the JSON-LD file, we have just the name, occupation, occupation_n, and occupation_cs. But in the generated RDF, the values are as expected with the proper language tags, or without a language tag in the case of the name string. This is, however, a bit inconvenient, or let's say not the way a JSON developer would do it, for specifically for the occupation, where we have a Japanese version, an English version, and a Czech version. The way a JSON developer would do it is this, and this is called a language map. And there is a support for it in JSON-LD. So we may say that occupation key here is mapped to the X occupation predicate, and it is a language container. So here we have a new keyword @container with the @language keyword as a value. And now in the JSON data, we have occupation its value is a JSON object, and in that JSON object there is a list of key value pairs where the key specifies the language and the value specifies the text in that language. So this is a special construct, which is how JSON developers would handle multi-language strings or multilingual strings, and JSON-LD is able to map this into proper RDF using the language map construct. We have seen JSON arrays quite a bit here, and let me talk for a while about what this means for RDF. In JSON, when we have a JSON array, the items in that array are ordered. When we have RDF, the statements are not ordered because RDF is a set of statements. So here we have a little bit of an inconsistency, because when we have the first example here, that we have Joe or someone with an ID Joe Bob, and they have three nicknames, Joe, Bob and JB. When we translate this into RDF using JSON-LD, it will be three statements with no particular order. Even though in JSON, in this array, Joe is first, Bob is second, and JB is third. This is because typically we do not need to preserve the ordering. So the default mode of translation of JSON arrays is that in RDF, this will be unordered. If we want to preserve the ordering, which might be a valid use case, we need to do this explicitly using the @list construct. And here we say that the nickname is a list, and the JSON array here gets translated into an RDF list, which preserves ordering. So this is just a note that if we want to preserve ordering of values in a JSON array, we need to do this explicitly in the JSON-LD context. Another problem which may arise from representing RDF in a hierarchical JSON format is that some of the predicates which are oriented in RDF, they always go from the subject to the object, are nested, or the relationships that they represent are represented in the JSON file in the other direction using nesting. An example here is from Simpsons. We have Homer here, who is the father or a parent of Bart and Lisa. However, we want to represent this relationship by the parent predicate in RDF, which goes from children to their parent. So we have Bart and Lisa, and they both have Homer as a parent. So we may be able to represent it in JSON-LD like this, which is again not how a JSON developer would do it, because it doesn't use the natural JSON object nesting. But it will produce the proper RDF. So what we can do is we can say that we will use an RDF predicate in a reverse direction. And then we can use JSON nesting and say that we have Homer, and within the JSON object representing Homer, we'll have the two JSON objects representing Bart and Lisa in an array, and this array will be interpreted in the reverse direction. So we may use the @reverse keyword for this. But still, it doesn't look like how a JSON developer would do this. This is actually how a JSON developer would do this. And when we first take a look at the plain JSON part of the data, we have Homer, who has children, and children is an array with two items, Bart and Lisa. And we need to translate this into the RDF data model using the parent predicate in the reverse direction, and we specify this in the context. So in the context, we create a new key or new mapping for children, and we say that the mapping for children is the reverse direction of the parent predicate. In JSON-LD, there is also support for named graphs. So here, this example actually generates a named graph with the id example.org/graphs/. JSON-LD/73. Now, we have talked about JSON-LD and its add keywords quite a lot. But from the regular JSON developer point of view, the add keyword might pose a problem because in regular JSON, you have no add keyword. So the question is if we can do something about it so that the JSON developer is not bothered by any add keywords. And what we can do is we can alias those keywords. We can rename those. So in our context now, we say that URL stands for @ID and type stands for @type. Therefore, in the JSON part, we say URL of this object is something and the type of this object is person and the name of this person is Greg Kellogg. So now it really looks quite normal in the JSON part. And what we did is that when we take the context and we produce RDF, we know that URL is actually ID. So this is the IRI of the RDF resource represented in the JSON file. Type represents the RDF type relationship, and the value person is mapped to the IRI fourth person, and the predicate name is mapped to the fourth name predicate or the name key. So actually now the JSON part looks like regular JSON, and when the context is also interpreted, the result is RDF representation of this data as it should be. Now, it may happen that the regular JSON developer says, okay, but I don't want to see the lengthy context definition in my JSON file. In that case, the context can be externalized. It can be published as a JSON-LD file somewhere on the web, and all that is left in the regular JSON file is one @context key pointing to the external context. If even this would be a problem, or if it is the case that we have JSON files published on the web and we just cannot modify them and we still want to map them to RDF, we might do this on the HTTP level. So in the actual file, it will be really just a regular JSON file. But on HTTP level, we'll see that the server will send us a link to a JSON-LD context. And therefore, if we understand this link, we might add that context to our JSON data and still see RDF. Now, JSON-LD is used in the wild, and the most prominent usage is probably for website or web page markup. So Google supports web page markup using JSON-LD script elements in HTML. So this is now the preferred way of adding markup to a web page. Historically, you could use microformats, microdata, or RDFA, which is yet another RDF serialization, which adds HTML attributes so that you can interpret that HTML as RDF. But now the preferred way is to add a script element to your HTML page containing JSON-LD using the schema.org vocabulary. So this actually is a real-world example. So if you take a look at this popular Czech eShop and you find a product there and you take a look in the source code of that HTML page and you'll search for application/LD plus JSON, which is the media type of JSON-LD, you will find JSON-LD usage there. So this was a way of interpreting JSON files as RDF, and this is the preferred way of actually mapping JSON data to RDF. Since there are many JSON developers out there who do not know RDF or just dislike RDF, this is a nice and convenient way of satisfying both sides of the wall. Those who want to work with RDF and take advantage of all that it brings, which is the immediate integration with other data sources and the mapping to vocabularies. And then they just point their favorite parser to a JSON-LD file And in the same way, they would point it to an RDF turtle file, and what they get is the RDF data model. And the JSON developers, which do not want to have anything to do with RDF, they will still see their favorite JSON format. So this is nowadays quite a popular way of publishing data on the web. Also, when you remember that when we talked about JSON, I said that JSON is used in the Czech standards of publishing open data, and I showed you this example. And when you take a closer look now, you'll notice that it is not just a JSON file described by a JSON schema, but it is also a JSON-LD file mapped using its context to RDF. So in the Czech Republic, when you publish open data, you should follow those standards for open data. And if you're interested in this and in more examples of JSON, JSON schema, and JSON-LD, you can go to this address ofn.gov.cz. It is in Czech, and it contains some examples of where JSON, JSON-LD, and JSON schema is used together.